welcome to Linaro Connect HKG 15. My name is Maxim Kuvyrkov, and I'm Toolchain tech lead at Linaro. This presentation is a tutorial/demo on how to analyze and investigate performance problems that are caused by the toolchain. So we are going to look at the initial conditions, what we have on the input. The problem will be that if you use a particular optimizations of the toolchain, which should in theory increase performance, we suddenly get bad performance on the board. We're going to look at how to make a reproducer script, reduce the problem to the minimal -O optimization level, then down to specific optimization, then down to specific instance of the optimization. And then we are going to try and figure out how compiler can avoid the problem and generate better code. And finally, we will go through the checklist of what, as a user, as a compiler user, you can give to the compiler developer so that developer can go ahead and improve the compiler and the toolchain. So, in the initial conditions, we have a compiler. We have some piece of ARM hardware, and with one set of compiler flags, we get 5,000 points on the benchmark. With the slightly different compiler flags, we have 3,000 points on the benchmark. That kind of performance difference is very big. Usually it is considered to be a regression if performance goes down by 10%. In this case, we have something like 40. And we can reproduce the performance problem stably. So if we run 10 times the benchmark, we will get very similar results for those 10 runs. First, to start investigating the problem, we need an automatic way to reproduce it. So we are going to look at what a reproducer script looks like. The basic things it should do is that it should compile benchmark, or the code you are interested in. It should copy it to the target, execute on the target, look through the output, and give you a concise result of what the performance is. The script that we are going to be using for this demo is available at linaro.org. So there are some snippets which you may want to use in your future investigations. So feel free, go and look at it. Let's look at an example of what such a script can do. How do we reproduce it? So we have compiler, we have some C flags, we have a board named Chrome, and we have a small function which is called try, which compiles the benchmark, copies to the target, runs it, and post-processes the result. Remember that you don't have to do this inside of a text file. It can be much more convenient to start investigating by copying this part, copy and paste that part into your shell, and then you suddenly have a shell command try, which you can give compiler arguments, which will do this and inside your interactive shell. So don't think that you only can use shell functions inside the shell script. Type them in your terminal, and then you have a very easy way to reproduce a problem. So our first step is to, in our optimization, so in our initial conditions, we have the problem occurring at -03, F3 vectorize, F unsafe math optimizations, F prefetch loop arrays, but it doesn't occur at -02. We get 5,000 points on the benchmark if we run at -02, but we get only 3,000 points if we add additional optimizations to our benchmark. Unfortunately, this is the only part of the demo that is not included in the current version of the results here. So we want to try, instead of trying and investigate what the problem is at the -03 optimization level, so let me pause here. Questions so far? Okay. Everyone knows what is the difference between -03 and -02. Who doesn't know?
I think the best question is who knows?
Who knows?
Yes.
Yes, who knows about -02 versus -03? So
In which version of GCC?
doesn't matter. It's the ideology question.
Oh, that one. Okay.
Yeah. So compiler has several optimization levels. -00, O stands for optimize. 0, 1, 2, and 3. At -02, consider it to be the standard optimization level, which is stock for most of the software compiled out there. -03 makes compiler work a bit harder and enable more optimizations, which generally can increase code size, but they will provide better performance. Classic example is rope unrolling. It is, we will generate faster code if we unroll loop 3 times, rather than have just a single iteration of the loop in the code. That will increase the code significantly, code size significantly, but performance should improve. The reason why we want to reduce to -02 is because -03 has all the optimizations that -02 has, plus some more. -02 has everything that -01 has, plus some more. So the least amount of optimizations compiler performs, the more they are interested to the compiler developer. Optimizations that run at -01 should run almost always perfectly, because they present at all optimization levels. So if you have a problem that only reproduces itself on -03, compiler developer might might make it a lower priority to fix if he has or she has an optimization that produces better performance at -02. So -02 optimizations always get higher priority for compiler developers to fix than -03 optimizations. If you can reproduce problem on -01, that's even better. Yeah, so performance regressions at -03 are tolerated because sometimes they can be too aggressive. So right now, we can go and try compile our benchmark with various at the various optimization levels and with various permutations of the input flags. So this is what we get on the input, right? And comparing just with stock -02, we get more than twice the difference in performance, right? At dash 02 we get 5,600, and at what's supposed to be very nice optimization flags, we get only less than 2,500. So what we do, we go and run our try function, our reproducer function, in a script that tries all permutations of dash 03, dash 02, dash 01 flags, with and without f3 vectorize, with and without f unsafe math optimizations, and with and without perpetual parades. Unfortunately, demo gods are not with me today, so I'm showing you pre-processed, pre-generated results. But otherwise, running these results are carbon copy of what I got from the real hardware several days ago. So, looking at these optimization flags, can you guess which of the flags is causing the regression? What are your opinions? Yeah. It takes some looking into this. We can see that F3 vectorize, we have both bad and good performance with it, so it's not the one causing it. Unsafe math optimizations, again, right, so F3 vectorize, we get both good and bad performance, same for unsafe math optimizations. But if we look at F perpetual parades, suddenly if we remove it, performance goes up. Let's look at the other optimization levels. Same happens for dash 02, so we have perpetual parades as primary suspect. But if we look at dash 01, we have good performance both with and without it. So we need to do some more investigation. How do we do more investigation? We can compare assembly, right? We can make compiler generate code for two versions of the compiler flags and look at what the differences are. Yeah. Okay, going back to the presentation. If we compare those two assembly files, we would have on the order of several hundred differences in the two files. Ivan, can you bring up? Yes, so let's do it here. So show us differences between
What? Is it to run one or?
Run the script, and the script will generate the files.
Yep. And the error message is fantastic.
Okay.
To read or code.
So now we want to try and reduce the problem down to a specific optimization. Because looking just at assembly code, which are completely different, doesn't give us a clue of what difference is, of what is causing the problem. Another reasons why we want to reduce problem down to optimization. Compiler has many dozens of maintainers, and generally every optimization in the compiler has a specific maintainer assigned to it. And that person, if you know who it is, if you know who to ask and record problems to, is much easier to deal with than the general compiler or toolchain community. So you want to figure out what optimization is causing the problem. The way to do this properly is to disable optimizations from the end. Compiler works as a pipeline. It gets source code on the input as input, and then it passes through one optimization, second, third, fourth, and each optimization is run after all the previous ones. They are ordered in a particular fashion, but the thing is, earlier optimizations, if you disable them, will give a very different result to the subsequent optimizations, so that the problem that's actually causing the regression might not occur if you disable some of the earlier optimizations. So if you want to figure out which optimization in the compiler is causing the problem to your test case, you need to disable them from the end. If there is a problem in the register allocator, it can easily be masked by loop unroller. But disabling loop unroller optimization can easily remove the regression, and you will never find out that it was actually caused by register allocation. But if you disable switch register allocation to something simpler, and suddenly the problem goes away, you have a very good argument why it is that a particular optimization causing the problem. So we need to get a list of optimizations. There are specific flags for GCC which can show you all the optimizations that are on and off for a particular set of flags. And as you can see, there are plenty. It would be a tedious exercise to try and disable all those optimizations one by one, starting from the bottom. So we want to script this. There are several ways to get a list of all the optimizations that compiler does. We can use that output, which is generated by fdump passes. My preferred method is to ask compiler to generate dumps for all optimizations, and then use name of the files asking compiler to generate a list of all of the optimizations will give you this, a list of files which have a number and identifier for them. Number is the sequence number of an optimization pass, and identifier is name of the pass. So for each of the identifiers, there is a corresponding compiler option to disable that pass. So what we do, we dump we essentially generate a list of the file of compiler optimizations. Then for each of the optimizations, we go and start disabling them from the end. So this loop disables n last optimizations, compiles the result, and runs the result on the target. So here we generate a list of optimizations. Then we generate list of all the optimization passes. And then we start running benchmark. Disabling more and more optimizations. So at -02, -f prefetch loop arrays, we have bad performance. If we go to disable RTL splits, we still have bad performance. But somewhere around here, we start to get good performance from our benchmark. And it seems, where do we start getting different performance? It's here, right? Between these two tries. And the new entry is disable RTL shed2, which is a scheduling optimization. Compiler instruction scheduling reshuffles instructions in a way that are more beneficial for a particular processor. So if your ARM CPU can execute 2 memory instructions on each cycle, it will try to make sure that each cycle has no more than 2 instructions, so that if there are 3 or 4 instructions to load from memory available, he will try to, the compiler will try to push those into a different cycle. We already skipped through this slide. This is how we can get list of optimization flags. Either dump passes or figure out from the dump names. After we got to the, and we know that we have a specific optimization responsible for the performance regression, what do? We go and compare assembly generated by the 2 versions of the compiler, by the 2 compiler labs. So in here, we can still see that lots and lots of small differences with and without scheduling. So scheduler decided to move this, whether scheduling is running or not, it moves instruction from here to here, or from here to there, but way too many differences to figure out what can be causing the problem. This is a very long difference now. So comparing assembly at this stage gives us nothing. There is a feature which is primarily designed to be used by compiler developers, but it is also a very good feature for users of the compiler when they prepare bug reports. And this is compiler debug counters. What they do is that each optimization has a list of one or two or several debug counters, and limit a particular optimization to only specified number of instances to run. In case of loop unroller, the debug counter for loop unroller will enroll only first n loops it sees in the program, like first three loops, but it will completely ignore fourth loop or fifth loop it sees in the program. Questions so far? So let's try and see what debug counters are present in the compiler. This is a list of all the debug counters. And if we look for the optimization shed, which we are interested in, we have quite a few counters. We can disable scheduling on per function basis with shed func. We can disable scheduling on per basic block, which is shed block, or even at instruction level. So we can tell scheduler, schedule first 1,000 instructions, but keep everything beyond that to the way it was before scheduling. So let's try and figure out, play with the debug counters, what we can get out of them. So we start with 10,000. Which is pretty much means schedule everything, because there is probably less than 10,000 instruction in our small benchmark. We get bad performance. Let's go to 1,000. We suddenly get good performance. So the problem spot lies somewhere between scheduling instruction 1001 and instruction 10,000. At this point, what kind of search do we do to get to the binary search? Yes, we do binary search, which is why you want to have your reproducer script be accessible from a command line, so that you can do this step just in shell, try this number, try that number, and see what kind of result you get. You can even script this. Yeah, and so we do the binary search, and we arrive to a magical value of 3213. With that number, we get suddenly twice the performance than with scheduling one more instruction. So it's like one last thing, you schedule one instruction and bang, for some reason you have bad performance. What do we do now? At this point, we compare the assembly. That's the holiday. That's the whole idea. That's the grail of performance investigation. When you have this small of a difference, that gives you that much of a performance difference. And this is completely reproducible. More than that, I can tell you that there is nothing about this related to vectorizer. Even without not generating neon instructions, if these are simple load and stores, so the same problem. What are your opinions? So, at this point, what do you do?
Why the bug?
And compiler developer ask for what? So you have problem that your application runs bad. Is compiler doing anything wrong in here? So scheduler, what scheduler does is that in case of slow and fast, let's actually do it the other way around. So what happens if we do, what happens when we go from fast to slow?
Can you increase font size?
Say again?
Font size.
Enlarge the font size.
Bigger font size.
There's some more context.
Okay. Thank you for the comment, by the way. Right. So when everything is fast, we have instruction. We don't have that instruction, right? So we have -24, -16, -8. All is good. Then if we have -16, -24, -8, things go bad. The background, if you look at the assembly around this, the scheduler is actually doing everything right. We have D19 set here, so while this instruction is executing, we don't want to use 0, we want to push the use of that value, which is in store, as further down as we can, so that there is no pipeline bubble, right? This is what scheduler does. It arranges instructions so that they execute in parallel as much as possible. So scheduler does the right thing. It tries to push the use of D19 from here down to here, so that it has probably 6 more cycles to execute. So at this point, you go and look at your ARM optimization manual, or whatever documentation you can find. Or maybe call your friendly ARM architect and ask him. But eventually you heuristically can try and figure out that you can start playing with assembly, insert instructions here and there. At that point you are handcrafting assembly and seeing how that affects performance of your program. Turns out that on certain ARM processors, memory controller will be faster if it executes memory operations in order. So -24 means that we first get this memory location, then this memory location, then this memory location, right? This is in the fast case. In the slow case, we do middle first, then left, then right. So you can start arguing with the compiler developer that please try and make memory references in order of memory addresses.
Have you tried switch the direction completely. So then you push the D19 all the way to the bottom, and you still have a linear axis, but it's in the reverse order. Does that make it faster?
I believe I tried, and from my vague memory, it doesn't make it faster.
It doesn't make it faster than the linear case?
No,
Of-
performance is bad.
Ah, okay.
Which color is it?
This is Cortex A15. So if you look at the manual for Cortex A15, there is about this much that Cortex A15 has a hardware level 2 cache auto prefetcher. That's it. Turns out, what auto prefetcher is, I don't know. What it is doing, I don't know. But it seems like if I were an auto prefetcher, I would prefetch addresses if I see them in consecutive order.
But are these addresses in the same cache line? All of them?
They are all in the
You're close enough.
with the same address, whether they fall on the same. This is a loop, so it goes through memory. This is a benchmark that takes one array, multiplies by a number, stores into another array. So it's vectorizable loop. Very simple. Get value, multiply, store. And this is what you see here, multiply and store. Sometimes they are in the same cache line, sometimes they are not.
Most of the time they are.
Yeah, so most of the time they are in the same cache line. So, at this point, we looked at this assembly. We have some understanding of what is happening at the hardware level. We try and play with handcrafted assembly to try and get some more insight in what is going on. It turns out if we inserted instructions unrelated to memory between those two, performance would not be affected. So it's not like those instructions are fused into a bigger memory instruction. They are not. So at this point, you have quite a bit of information that you can start preparing a program report for the compiler developer. What you want to include is a way for compiler developer to reproduce your problem with the least effort possible. I know it will force you as users and as bug reporters to spend more time to prepare the bug report, but it is very difficult sometimes to reproduce problem in a new environment. At the minimum, compiler specify what hardware you are using, not just an ARM board, specify CPU, ideally frequency, or board make and model. Full source code so that compiler developer can recompile and make sure that the problem is not caused by a wrong library, a wrong version of the library you might have linked in or something else. And then everything that we generated through the duration of this presentation. So compiler dumps, preprocessed files, object files, which can be relinked into a final executable, assembly files, a good description of what you have done and what you have not done. Like, I have tested this on Cortex A15. I do not know whether this applies to Cortex A8. And submit that all in the bug report. One compiler engineer typically will start by looking at differences in the assembly to make sure that compiler can actually do something about it. if right now you cannot say that there is a bug in the scheduler, right? Because scheduler did everything right with the information it was given. It didn't know about this particular feature of a particular CPU model. Compiler engineer will look at the difference at assembly, run binaries that you have provided, recompile them to make sure that he can still reproduce the problem with a newer compiler, and start debugging and fixing the compiler. The amount of effort a user that is very significant, but also appreciate that the amount of effort to go into the scheduler or in the compiler optimization to figure out why it is happening the way it is happening and how to make it work better can also be very significant. For this seemingly small optimization, it took on the order of several months and more than 10 separate patches to the compiler to fix it. And it will be available in the next release of the Linaro compiler, in the next major release of the Linaro compiler. Even if you did everything right, there is a certain class of problems that compiler cannot fix. Most of these problems are, quite a big chunk of these problems are related to aligning. So if your application gets a little bit different layout in the memory, and suddenly your main loop is not as well aligned anymore, performance can get bad, but often compiler can do nothing about it. So be ready for the resolution of your bug that, sorry, yes, we see that this is a problem for you, but compiler can do nothing reasonable to fix this. For problems like this is not a regression. This is not a bug. It's a significant new feature. And significant new features will be available only in the next release of the compiler, which can be a year away. Especially if you're investigating a problem against an older compiler version like GCC 4.7, make sure that it is also reproducible on the very latest released version of the compiler. Because if it is not, then there is nothing to be done. And you might have to wait for several months, maybe even a year, to get the fix in a released production quality toolchain. So this is the end of the presentation. And now I first take any questions or any comments. And then I have several questions for you about what are your current processes with dealing with performance regressions, and whether you can integrate some of this process into your existing quality assurances and debugging processes. Questions?
Yeah,
go
this,
ahead.
this particular problem you found in A50E. Did you try it on any other architectures like A9 and is it still there or it's not there at all?
So the architectures I tried this on are A15, obviously affected. A57 also affected, not quite as much. So on A57 the difference is about 10%, which is still a reasonable number. So from, I believe I'm to double check A53, but I believe A53 is not affected. So far it seems that the big cores, so in big little cores, big cores affected, little cores not. Other questions? Okay, but what about answers to these questions? When typically do you notice code quality issues? anyone from the industry wants to share.
Performance or correctness?
Performance. Correctness you normally notice whenever you switch to a new compiler version. I'm sorry, correctness issues you find when you switch to a new compiler version. Do you have standard performance checking processes? Weekly benchmarking, monthly benchmarking.
Random benchmark.
You have random benchmarking. Okay, then let's wrap it up and thank you everyone for attending the session.